Hey, this is Mr. Boggs, and next to me is Sir Isaac Newton. Isaac Newton was a pretty important scientist, probably one of the most important scientists of all time, and he published his work in a book called the Principia. And in this book, he explained gravity and how the law of universal gravitation works. He explained his three laws of motion. It's probably one of the most important books, scientific books of all time. It kickstarted physics, and in fact, most of the formulas that you see in a typical physics book came right out of the Principia. So that's what I want to talk about today is Newton's three laws of motion. So Newton's first law of motion states that an object will remain in a state of rest or uniform motion unless it is acted on by an unbalanced force. So basically, what is that telling us? It's explaining what inertia is. And inertia is the tendency of an object to resist a change in its motion. So it doesn't want to change whatever motion it's already in. So if an object is sitting still, then it wants to remain sitting still unless some other force, outside force, acts on it. But if an object is moving, then it wants to keep on moving in whatever direction it's going in. Now, you've probably heard of Newton's three laws before, and you probably studied it many times throughout school. And so it may seem like it's kind of common knowledge to know this information. But sometimes we take for granted where we actually got this knowledge. In fact, Newton's three laws are pretty young. They're only, pretty new to us. They're only a couple hundred years old. But really, it started about 2,000 years ago whenever Aristotle started to describe motion. So it took us a while to get to Newton's three laws. Aristotle, he was a pretty smart guy as well, but a lot of things that he said were true about the world whenever he's making his observations. But he did incorrectly propose something about motion, and he said that for an object to remain at a constant speed, that you had to constantly apply force to it. And even though we know that that's not true now, it makes a lot of sense how he actually came to that conclusion. So if we actually look at what he observed at the time, so if we have a spherical object, aka a ball, and we apply a force to it, what happens to it whenever we apply a force? Keep in mind, no one had described gravity, or friction, which we both find to be common knowledge now, but it wasn't always common knowledge. So he didn't know about the force of gravity or friction acting on an object. So what did he observe? If he's rolling the ball, what happens to it? It goes for a little while, and then eventually it stops. So you can't actually see gravity applying a force to it, and you can't actually see friction applying a force. So he had to keep adding force to keep it moving at a constant speed. So it makes a lot of sense where he got this. And so I just want you to think about that a little bit because that's the great thing about science is that we're constantly seeking the truth about things. And just because something is known to be true for a long period of time doesn't mean that it can't change. And so that's what happened. We thought that you had to constantly apply force for over 2,000 years. People, that was their truth at the time. So Newton's first law, let's give some examples of that one. So Newton's first law, me and Newton here, Isaac, we went to outer space. So we're just sitting in outer space. Isaac's smiling at me for some reason. We had no gravitational forces acting on us, no friction, and I just dropped him in the middle of outer space. He would just sit there, kind of like he's doing right now. So he's just sitting there in the middle of space, no outside forces are acting on him. So that's Newton's first law. An object at rest will stay at rest. But what happens if I apply an unbalanced force to him? So if I applied a force to him, he would just start moving away from me, and he would just keep going at a constant speed on forever and he's still going until an unbalanced force acted on his body to change his motion. And so that's Newton's first law, and it's also called the law of inertia. Newton's second law of motion is probably one of the most important laws of motion that Newton came up with, because it gives us a lot of formulas that we can use to describe motion. So basically what Newton's second law, it describes the relationship between three variables: force, mass, and acceleration. So it states that the acceleration of an object is directly proportional to its force acting on it and inversely proportional to its mass. So what does that mean? If we break down this sentence here, let's just look at the first part of it first. So if we cut this sentence right here, we just look at the first part of it all the way to here. So acceleration of an object is directly proportional to its force. So how does force affect acceleration? Well, if force goes up, then acceleration is going to go up. If force goes down, then acceleration goes down. So let's look at an example of that. If we have two balls here of equal mass, and we applied a force to the first ball of 1 Newton, so you can see how fast it goes, how fast it accelerates. But if we were to increase that force and we gave it a applied 5 newtons of force to it, you can see what happens to the acceleration. It goes up. So if force goes up, acceleration goes up. If it goes down, then acceleration goes down. The second part of the sentence here, so if we just look at the acceleration of an object is inversely proportional to its mass. So how does mass affect acceleration? Well, if we look and we have a golf ball again, we applied a 1 Newton force to it, you can see what the acceleration looks like. But if we increase the mass of that ball and we applied the same force, still the 1 newtons of force, what happens to acceleration? It doesn't accelerate quite as fast. So if mass goes up, then acceleration goes down. If mass goes down, you have a smaller object, then the acceleration goes up. So that's Newton's second law of motion. Newton's third law of motion, and this is also known as the action-reaction law. And so it states that when one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. So if I'm this guy and I'm pushing on the wall is applying the same amount of force back on me. So if I'm applying 20 newtons of force to the wall is applying 20 newtons of force back to me. So what would happen if I applied more force than that wall could apply back? Then I would end up knocking the wall down. So you may think that sounds kind of funny, like that a wall can't apply a force back to you, but think about you applying a force to a wall if you're standing on a skateboard. So you're applying a force back, and so what would happen to you if you applied that force to the wall? Then you would push and you would go in the opposite direction. Another example of that is how rockets work. So with rockets, you have the fuel being pushed out of the bottom side. So you have one force in this direction by the rocket pushing the fuel in that direction, and then the fuel is pushing the rocket in the opposite direction. So whenever you light that fuel, it's going to send it off into outer space there. My last example of Newton's third law, just because it gives me a good example. So my last example of Newton's third law are falling objects. So we've talked about gravity already, and how gravity is a force that pulls objects down. So if we have our flying squirrel here, he has his flaps that he increases the amount of air resistance on the bottom, allows him to stay in the air a little bit longer. But how does Newton's third law play into this? As gravity is pulling an object down, it accelerates faster and faster and faster. And as it picks up speed, it's applying more force to the air that the object is falling through. So as you go faster and faster, you're getting more and more air resistance on there, and you're slowing down you're slowing your acceleration down. So eventually you'll reach something called terminal, sorry, I can't, right here, terminal velocity. And what terminal velocity is whenever the force of gravity is equal to air resistance. So as you speed up and you go faster and faster downward, you're increasing the force here. When those two forces are equal, then you stop accelerating. That's terminal velocity. It doesn't mean that the object stops falling. It just means that it's going at a constant speed down. And so that is Newton's third law. And a lot of times we get ideas from things that we see in nature, and we steal those ideas and we create our wingsuit to go skydiving. So if we didn't have an atmosphere, we didn't have air resistance, we didn't have Newton's 3 laws governing us, then we wouldn't be able to do things like this and shoot through the air. And so I hope this video was helpful. And I'll let you enjoy the rest of this video real quick, but I'll see you guys next time. Thanks.